Professor Simmons here. I'm going to talk to you a little bit about uncertainty in measurement and show you the Matlab script and show you a little bit about Matlab to help you with this this computer programming lab for PH2011. So let me bring up Matlab here. So if you're looking at this video and working on this, you should have installed Matlab on your machine by now. If not, there's some directions posted on Canvas about how to do that. So before we, a couple things. One, the reason that we're doing this is if we were able to meet in person, there's a version of this lab where we look at a bouncing ball and we collect a set of measurements of the ball bouncing, the time that it takes to bounce, and we use those time measurements as a data set, and we can look at the statistics of those, and that gives us our uncertainty in measurement. That's sort of what we examine. In this case, instead, we're going to use U as a clock, and you're going to count seconds and build up a data set of 100 seconds. And we're going to look at the statistics of that data set. And by doing it on the computer, you can do it kind of from anywhere. And also, it lets us do some things in Matlab. We can plot it. We can look at it in a little more detail than we would be able to do if we did it manually or did it in Excel. So before we get into the nuts and bolts of how this script works, let me show you a little bit about the lay of the land with Matlab, because I suspect most of you probably haven't used Matlab before. So Matlab is a programming language and environment that you have access to as a student at MSOE. And many programs, I should say many majors, have you do stuff using this language. So we're going to kind of overlap, connect, interlock with some of your other courses. So I think this is a totally reasonable thing to do. If you haven't used Matlab yet, you'll probably use it and be using it this term, if not in a future term soon, to work on your coursework. So it's definitely a good skill to have in your toolkit. So like a lot of programs, there's a menu up here with various functions, and you'll poke around in there and learn how that works. But let me just point out kind of a couple of the big things that we're looking at. There's the current folder also listed up here, this bit on the left, and the way I have it set up. That tells you the directory that you're operating in. So the script and stuff that you're running needs to be in that directory generally. This window in the center is your editor window. So this is where the program, the script is that you're working on. That's kind of the heart of where you'll spend probably most of your energy. Writing the script, making changes in this center section. This thing down below is the command window. So you enter commands here. So you can execute things, you can do calculations. You may find that this works pretty well for doing your homework. You can, compute numbers down in the command window. And then this thing over on the right here is the workspace. So this is basically like the memory of all the variables that you create. So for example, if I create down here a equals 1, you'll notice that appears in the workspace. And so I can type a and it will tell me 1. Or you can also click on this and it'll open it as kind of a spreadsheet and you can see the value. So if you have multi-dimensional objects, you might have a list or a table in here when you click on it. Okay, so that's kind of the big picture, the 1-minute introduction to Matlab. So let's apply it to this problem of uncertainty. So like I mentioned, rather than recording a bunch of ball bounce times, you are going to use yourself as a clock. So you're going to do this for 100 seconds. I'm not going to do this for 100 seconds to demonstrate it to you. I'm just going to do it for 10 just to show it running. But I should say, to actually run the script, you notice you click on different sub bits of this. If you have 2 of these, it'll break it into chunks. And you can execute each chunk one by one. And there are different ways to do this. You'll notice at the top in the editor window, if you click run section, that'll run the one section. Run will just run the whole thing. You can also click Control Enter, and it'll run a section. So let me run this first section, and we'll count 10 seconds just to show you how it works. When you run this, you'll run it. It'll go for 100 counts, so you'll have a better data set than I will. But so if I click Control Enter, it starts. It spits out some text here, just to kind of get you started. And then I'm going to click Enter. So I'm going to 11 times to record my 10 measurements. So I changed this so that it stopped just after 10, just so you don't want to listen to me count 100 seconds. But that gives you a feel for how this works. It's quite simple. Now if I click on this times vector, you can see the contents. It's a list of 10 numbers. You can see they're not all the same because I have some variation. I have some uncertainty in my time measurements. So the next thing that we're going to do is after you record your measurements, so actually I'm going to swap in here a data set that has 100 measurements so it'll look just like yours. So I just loaded that in. The next section, if you run it, is going to spit out some of the measurements that we want. So you'll notice it returns the average and the standard deviation. And depending on how familiar you are with calculating standard deviation, it's done in two different ways in here. One, it's done in a sort of step-by-step way where we subtract off the mean from each measurement, we square those differences, we take the average of that, and then we take a square root. And then we compare that with this built-in function std, which will take the standard deviation of your times vector, all in one operation. So this is just to give you some confidence that that you could construct this yourself if you wanted to from sort of basic operations, and it shows you how to go about that. Now you'll notice that these two measurements are slightly different, and that gets into a detail in the standard deviation calculation. The difference between a sample standard deviation and a population standard deviation. And if you'll notice there's some text in here. This green, these are called comments. So this is code that doesn't get evaluated. It's just to help you, guidance. You can put comments in your programs to help you make them more easily understood. And so if you study this script, these comments get into the difference between standard deviation and sample standard deviation. And so I would encourage you to look at that. Basically, it amounts to the sample standard deviation you divide by n-1 instead of n when computing the average. And that will give you a slightly different number. So if we correct for that, we'll get the same thing as the built-in standard deviation. And so you can see that here when you execute this section. Notice now we get the same thing as we did from the built-in function. So that's where that discrepancy is. And then there's one more calculation in here. So while the standard deviation basically tells you how much any individual measurement fluctuates, the standard deviation of the mean tells you how much the mean fluctuates. And you'll notice that it's a much smaller number, and that's a way of saying that you know the mean better than you know any individual measurement. And to compute this, what you do is simply divide the standard deviation by the square root of the number of measurements that you take. So we had 100 measurements, so if you divide your, in our case, we would divide that standard deviation by 10, and that would give us the standard deviation of the mean. So you'll notice it's 10 times smaller than the standard deviation. So usually when we're talking about standard error, that is what we are talking about, the standard deviation of the mean. And I would encourage you to study Dr. Wright's reference video on these statistical concepts. He goes into a lot more detail on this. and I have that posted in Canvas, as well as take a look at, study the lab document, study the comments that are in the script, to make sure that you have good command of these different definitions: standard deviation, mean, sample standard deviation of the mean. They sound kind of all the same, or they can, so it's important to have a good understanding of the subtleties of how these things are different. Now, so that's kind of the statistics that we can compute from our numbers. The next thing is one of the features that's really nice about doing this in Matlab is that we can plot this. So this discussion of error is based on the error being distributed. So there's a function, the Gaussian distribution. You may have heard of this as a normal distribution or the bell curve or something like that. You may have run into this in statistics or another math course, but basically this distribution describes random error. And it's specified by the mean and the standard deviation are sort of the pertinent factors. So if I run this section, it will create a plot where the x-axis is time, the y-axis is how many measurements fall in each of these time bins, and this red curve is that Gaussian distribution. So you'll have heard a rule of thumb, something like, so if you click on the arrow in the upper corner, it'll put the figure in your Matlab window, so it's not a separate window. But that Gaussian distribution plotted on top of the distribution can give you a sense of how good your measurements correspond to this Gaussian distribution. So you can see it looks similar. There's a spread, but maybe your measurements may be asymmetrical, or you might have a fair amount of outliers that are far away, or something like that that would indicate a difference between the Gaussian distribution and your measurements. That's totally fine. The error of a person trying to count seconds, the error in those time measurements, is not necessarily perfectly random or perfectly described by this Gaussian distribution, and there's going to be fluctuations. One other thing to note here, there's a couple lines. So these blue lines indicate one standard deviation away from the mean. And so one of the qualitative questions that we can ask is, does this rule of thumb hold that most of your data, 2/3 or so, fall within one standard deviation? So you could inspect this figure and count up how many data points fall between the blue lines. And that would be a way to kind of gauge if your data is Gaussian. And then, so you can also, you can look at the code and how this works to give you an idea of how to plot histograms, how to plot Gaussians. The purpose of this is not to have you have to be able to do this, but it is to kind of expose you a little bit to how this is done in Matlab. Just getting your toes wet in terms of getting a little bit of exposure to how this works. And how to plot the lines and how to plot the histogram, etc. These various, here's the histogram statement. Here's our Gaussian. Here's the lines that we plot, etc. So you can kind of use this code as a reference. So, and then you'll notice the fourth part in here, there are some questions. So, qualitatively, you'll have to evaluate this for your data, but does it look Gaussian? You can examine if you got faster or slower. Maybe while you were counting seconds, you got you sped up. You wanted it to be done sooner or something. You can just plot all the data to get a feel for that. And then this rule of thumb, does 2/3 of your data fall within one standard deviation? You can look at that a little more quantitatively. So there's a snippet of code at the bottom of the script that will do that for you. There's different ways to do that, but it shows you a for loop, which is sort of a fundamental programming method. So you can look at that and see with your data if it agreed. And then this spread, all this that we've been talking about so far, is basically random error. And there's another kind of error that we have to keep in mind, and that is systematic error. So while random error says something about how much variation there there is in your measurements. Um, Systematic error would be some issue that's common to all your measurements. So if you were, for example, measuring length with a ruler, where the ruler was cut off or short or something, all your measurements would be off, and that would be an example of a systematic error. So in terms of our time measurements, your average time, does it tend to be fast or slow relative to 1 second? That would tell you if you're systematically fast or slow relative to if say 1 second was the actual time. So for me, you can see my distribution is it's a little bit more than 1 second, the average. So that would be an indication that I am systematically slow relative to time equals 1 second. And then the bottom of this has a couple extra tidbits of code. So this loop here will count how many measurements fall within one standard deviation. You can kind of look at that and see how that works and have that filed away. That will help you, answer this question, but also you can kind of use this as a programming reference. And then you can also, there's a bit here that will plot all your measurements. You can use this to tell, if you're speeding up or slowing down or what's going on with your measurements. So it's another way to examine the data kind of all at once. The moral of the story with this being that plots can be really powerful. So if there's a way to plot your data rather than just talking about it, try and plot it. Great. So hopefully this helps you with the lab. So use this in conjunction with Dr. Wright's reference video and the lab document. And if you have any other questions, we'll talk to me and we'll get it figured out.